Well, hi. So yeah, we already heard the topic, and my name is Phil, and I will talking a little bit about how physical objects affect the performance when I'm sketching on them in augmented reality. And so why is sketching in AR an interesting topic anyways? So think of this. 3D printers are now available everywhere. Basically, you can buy them in a hardware store. And stuff that people often want to do is attach their newly created objects to existing ones in the world. I mean, for example, we have the golf club that you wanted to attach your sensors to, right? So I went to Thingiverse, where makers share their models and their projects, and basically had a look for different objects they have there. So, I mean, it's almost Christmas, right? So chocolates are in the store, so it must be close. So this is a Santa's hat that you can print out and just put on top of a champagne bottle. Or if you burn your hands on hot coffee mugs, you can use a sleeve like this where that protects your hand when you're holding it. Or yeah, a nightstand for your Apple Watch that looks like a classic Mac. And I quite like this one. That's a door stopper that you can just attach to the frame, and then it keeps the door open. And a family father designed that actually to prevent his little ninjas of running through the house and slamming doors and smashing their fingers. So he designed that, could just attach it to the door frame and lock the door. And what all of these examples have in common is that they require the fitting of a virtual object to an existing physical object in the real world. And that's no problem if you have the model, if you have the design, you can just send it to the 3D printer, wait for a couple of hours, and then yeah, you're done. And there's a large library of things like that for example, Thingiverse. But those are usually then for specific objects, so we know the exact size. So for the Apple Watch, that doesn't change from person to person. Or they're flexible, like this coffee sleeve that, well, depends on how big your coffee mug is. If you have a specific idea or it doesn't fit exactly what you want, then, well, what do you do then? Maybe, yeah, if I want to attach something here to this lectern, it has a quite weird shape. If I want to have a light here, lighting things up, probably won't find something like that on Thingiverse. So in that case, well, how do I get the idea that I have in the hat into a model that I can send to the 3D printer? And what you currently would have to do is, yeah, measure the physical environment. So take this all in, take all the measurements, then go to a PC and rearrange your object there. So basically you're designing in a completely different context and where you want to use it. And well, what if you then mix up scales, whatever you designed in meters instead of centimeters or something like that? And that happens because you don't have really the context. And now wouldn't it be great if I could just go to the door frame and design it, the object where I want to use it, and use the properties of the physical object while I'm designing that? And that's what we envision or want to see or in sketching in AR. There I could basically take a pen, go there on the door frame, use that sketch how my object should look like, and I can directly in AR see how the object would look like, and I can design, well, how far open should the door be, and stuff like that. So yeah, to look at a couple of projects that work in or go into a similar direction or sketching in AR. This is from last year's SIGCHI, where they used a 3D extruder pin that you can just draw in midair, but they combined it with AR and helped people actually recreate wireframe models that you have. Because they found, well, if you just see the model once and then try to replicate it, you won't get it right. So maybe for the dolphin, the base is not large enough and it tips over and stuff like that. So what they did was analyze these wireframe models and then calculated in which sequence the strokes have to be that I can recreate them, and then just showed it in AR so people could yeah, follow those lines and then draw it like that. And well, the results stood up right, but as you can see, well, they're still a little bit wavy and yeah, not very smooth. To change that, this is from this year's SIGCHI, where they used a robotic arm that actually then prints out the virtual model on the back of a drawing platform, while on the front you could use this controller to actually manipulate the design or start using that, and depending on the position of the designer, the position would shift and the robotic arm would take over and print it out. So to use physical props for personal fabrication, I think this is a prominent example, which is a mixed reality display. And if you take a physical object like this, well, stick of glue, you could hold it behind the surface and with a scan you can use that object to actually manipulate the virtual one. So stick it in there to create a hole that later on the stick would fit exactly in there. But coming back to sketching, Aurora et al. Looked at, well, how do physical surfaces, flat physical surfaces affect the drawing performance? So they let users draw circles in VR without any guide on a flat surface, or even just using a chalkboard and drawing on that. And they compared the performance from that. What they found was that just putting on the virtual headset and visualizing the stroke instead of seeing it in the real world decreased the performance or the accuracy by about 20%. And then if you remove the physical surface, it gets even lower. It's then further 27% that the accuracy of that stroke is decreased. And in the second experiment, they showed visual guidelines. So for example, just showed a flat surface in VR that people should draw the circle in, or they showed the actual circle that they wanted people to replicate. And they found that, well, showing the surface already improves the accuracy, but showing the stroke makes it then even better. The resulting circle was much closer to that. But it was less elegant because people were correcting their strokes a little bit more. So to look at that, what we've already seen is that, well, surfaces help, but really the precise 3D sketching on physical objects that are not flat, that has not been looked at, and also not looked at in AR. And so that is what we set out to do. And for that, we'll first, well, look at the physical object. What properties do physical objects have to guiding such lines? And then we evaluate what the different guides have an effect on the performance when I draw around in AR. So looking at the different types, how a surface can guide the stroke, there are a lot of things how objects can, well, affect that. The material is important, whether it's a hard surface, whether it's a soft surface, rough or smooth, and stuff like that. But instead, we want to focus on the local features that help me to guide or draw a particular line. So the most basic one is, well, just having a flat surface. If I want to draw on here, I'm restricted. I can't go into the physical surface. I'm limited by that. But then once I get to the edge here, well, this is a line that is more, well, described by having a physical different shape. So, or for example, on the edge of a coffee mug, that can slip off on those both sides. On the other hand, if I have a concave edge, that's more physical assistance. I can't really slide off that often, and I'm constrained more to that area. And then it doesn't only have to be a physical change of the surface. It can also be a line that I see, whether it's something printed on there or something, well, not intentionally aligned, but the water level in the bottle that can indicate, okay, where that you might want to follow. And so far, all of these are physical objects, but in AR we can also place purely virtual objects in the world. So think of the IKEA kitchen that you want to set up in your new home, and you want to draw maybe on there where the sink is going to be or stuff like that. So all of that, these different levels can also be purely virtual. And here I don't have any physical guide. I can penetrate the surface there. So what we did in our study, we wanted people to draw around physical objects and look at how the different guidance types affect the performance. So, and to remove all influence of the orientation, how people hold the device, interact with that, we fixed them upright on the table. And that also allowed us to use virtual objects without having to worry about, how do I hold a virtual object and rotate it, for example. And we used a cylinder object and a cuboid to have a continuous stroke, a circle, and a non-continuous stroke where I have a square that I have to draw. The size was more like what would fit in a normal 3D printer, and the pen you see here in front is attached with markers that we can use then to track it with a motion capture system. And the tip of the pen is also a spherical marker for two reasons. One, to have more precision in that particular area, and also if the visualization from the headset just shifts a little bit, it still looks like it comes out of the tip of the pen. So this is our setup. We have our participant sitting in front of the object and within the tracking volume of the Wagner system. And the HoloLens were used to visualize the virtual strokes. And we used for this image we have there to roughly synchronize the object, the coordinate system of the HoloLens and the Wagner tracking system. So the participants were not allowed to stand up and move around. They were asked to be seated and had to draw around all of the objects for 5 strokes. So, and for each of the strokes, after processing them, we calculated 5 different measurements and compared them to the optimal stroke that they could have. So the first calculation is the overall deviation or the mean deviation in 3D. And then we looked at from different perspectives onto those renderings. So one is the X and Y direction, or the horizontal direction, basically looking from the top, how far did they deviate from that object. And then also in the Z dimension, so how much did they deviate in the vertical direction. And for that, we looked at both the overall deviation that they had, but also directed whether they were more drawing above the target line or below the target line. And also we calculated how long they took for the stroke. For those comparisons, of course, we had to adapt the physical recordings a little bit, because due to the spherical pen tip that we had, it was not possible to really draw precisely on there, since the stroke came from the center of that tip. So we had to adjust it by the size of our tip. So looking at the results, it's clear that the physical objects have a much less deviation when drawing on them compared to the virtual ones. So in fact, the physical ones are about 5 millimeters, while on virtual objects it's almost twice as much. And overall, the guides help for drawing the best line. And in fact, on the physical object, the concave one is better than having no guide as well, showing on that. And this same tendency that physical is way better than virtual also was apparent for the other conditions. So if looking from the top on that, well, the virtual ones are much more spread out. And when we're looking at the directed deviation, we can see that for the physical object, people drew almost precisely on the target line on that height, not much deviation there to the top or to the bottom. But for the virtual ones, it's interesting that if there was a guide present, so convex edge, concave edge, or a visual line, they were drawing more above that line. Duration was the only place where the shape had an effect. And in fact, yeah, drawing around the cylinder was about 2 seconds faster than drawing around the cuboid, which probably you have to stop at the edges and or the corners to draw around that. And while there was no statistically significant effect of the different surfaces or the different guides, looking at the data, well, it seems like the physical concave one could be a little bit faster than the rest. It is at least has less spread in the data compared to the others, while the convex one is a little bit more spread out. But we haven't found any statistical significance in that area. So what we also thought of, that the performance, whether I'm drawing on the front of an object and on the back of an object, might also have a big effect. So what we did was split the recording into a front-facing half and a back-facing half, and calculated again what now the new side variable had an effect. And in general, well, party outside, in general it was that the front deviated less than on the back. But there were no strong interaction effects that were related to the interaction with surfaces or the different guidelines. Overall, it became apparent that whether it's a physical surface or a virtual surface has much bigger effect than whether it's on the front, back, or which guide was used. Especially when you look at the renderings of the square, it looks like the side is very, or a little bit more accurate compared to the front and back, and the front and back is a lot more spread out. So what we looked at was how the directed, let's call it directed XY deviation behaved. So we gave points that were inside the object a negative value, and points that were outside a positive value, so to see whether it was drawn mostly inside or mostly outside. And there we can see that, in fact, on the front of the device, the users were drawn mostly outside of the object, while on the back of the device it was much more spread. So on the circle, a little bit more inside, while on the square also outside, but much closer to the actual line inside and outside. And possible reason for that is we decided, or we occluded the stroke when it was hidden or would have been hidden in a real physical world, so if it was behind or whether I was inside the object. So it was much easier to decide whether I was in front or inside the object. Which points out, the visualization is quite important, and well, in AR you have the possibility to visualize things that are not seen, so showing that. So putting that all together, physical objects definitely improve the drawing accuracy, and guides can help to correct your path and stay in the areas. The non-continuous shapes take a little bit longer, but otherwise there's not really a change on the accuracy. There's less accuracy on the back of the device and of the object than on the front. And the sides from the square rendering seem to be more accurate and might be better to align to those. So the changes that we found were, well, quite small, but we only also had a smaller object, so they might increase if you have larger shapes, larger areas that you draw around. So what to do with all that information? Think of, you want to draw in mid-air, and you want to attach something to the door frame, like the door handle that we talked about. And a correction there is quite important. I think the talk after me will go into more detail about that probably. So we need the system to somehow snap your strokes to the line or to the object you want to draw it. And so in the example of the door holder, if I want to draw on the frame and then lift off into mid-air, the system needs to be able to decide, okay, does the user still want to be attached to the door or want to draw mid-air? So in what area are we still in the area of reasonable deviation, or when it's in intended deviation into mid-air? So from our results, we created groups and calculated the distance in which 95% of the points that we recorded would be lying. And yeah, the main grouping there is into physical and virtual objects. We can see that while for physical objects, most of the points lie within about 11 millimeters, for virtual objects it's almost twice as large, or over twice as large, an area where 95% of the points are lying. Since the guides had an effect particularly on the physical objects, we also separated those. So while on physical objects, if I don't have any guide, the 95% of the points lie within around 15 millimeters. If there's a guide present, it's much less. It's below 10 millimeters where you want to draw. And for since the front and back on virtual objects seem to have an effect, we also looked at that. And while on virtual object the front is about 20 millimeters, the back is a little bit larger with 25 millimeters that span that area. And on the physical objects, there's essentially no difference between the front and back. They're very, very close together because you can orient from the haptic surface that you have. So where to go from here? So our experiment was very rigid. So we had a lot of things that we kept still to be able to only look at the effect of our different guidance types. So look at other factors, the different materials that you use, different sizes, how do they affect that, and the orientation. And yeah, if I can draw in AR, look at bimanual task. If I, for example, hold this coffee mug and draw on that, what different strategies are there? Are people drawing around more like this or rotating the object while sketching on that? That is something you can look into. We had, for practicality reasons, also a spherical tip on our pen. But it's something that we want to look more deeper into on, well, how does this affect the drawing? What is the mental model of drawing with a spherical tip there? And in AR, you also have the possibility to visualize things that would normally not be seen. So information on the back of the device that I can look through that. Our pilot test suggested that it's quite confusing to just visualize that line looking through that. But maybe there are other visualizations that help showing, well, what is there behind. And then, of course, well, now this was only for drawing a line. What if I want to create really a more complex geometry that has mass or more mass? Yes. So to sum that all up, we had the initial problem of if I have an idea, how do I get it into a model that I then can print out? And our idea what to do in that for that question is to use AR sketching. And so we looked at what different features physical objects really provide, and to draw on that, the local feature that classify a line, and classified that. And then that allowed us to, we implemented a system that allows us to draw in midair, seeing those strokes. And we evaluated the effect that these different types have on the drawing performance. And physical is there definitely the strongest factor, but the guides can also help, especially on physical objects, to improve the performance on a particular line. Looking at the renderings, look like, the front and back have different precision, especially on the virtual objects, and might be a little bit more spread on the back of the object. So AR sketching is quite an interesting field, in my opinion, and has the potential really to make the 3D model generation a little bit more intuitive, a little more in place. Thanks a lot.
To ask for questions because they're coming up. Thank you for the very interesting talk. My question is, have you investigated scenarios where people do both, do mid-air sketching and sketching on surfaces? Because I think this is the usual case. And I would be interested if you know what people do. Do they first do all the sketching on the surface and then start drawing in the air, or do they show a certain behavior?
We have not looked at that particularly in this setup. Because we wanted to more focus on how well can they actually draw than on the physical object. But it's a very different or very, very interesting question to see that leap from the physical object into mid-air. And it's something we have in mind to look at more further. Here it was really limited on the physical object. How well could I draw that before I'm leaving off, and not the whole system, yes.
Hi, thank you for your talk. Very interesting. My name is Adrian. Just a question on the accuracy. I mean, you said like it's about 1 centimeter, 2 centimeter of error that we have. I mean, and in that range, I would say there's no application case, perhaps. And currently people would probably scan the surface to get a proper surface representation and then work in virtual environments completely. But I'm wondering, in particular in the virtual case, in both cases, whether you have tried to check where the errors come from. One source of error is certainly the tracking system. And I've seen you have been using the
Viken motion tracking.
The Viken tracking, but you have been using the Microsoft HoloLens as a device, which has its own tracking. How did you get them aligned? That's one of the questions, and it goes further into the question for the VR condition. You have most errors in depth, so for front and back faces, which might be related to not accounting for eye positions and eye distances, because they have a huge effect, and also certainly the resolution that you get between your eyes.
Yeah. To go step by step, to align the different coordinate systems. The evaluation was done with the data we got from the Viken system. The visualization we showed through the HoloLens was, well, not completely detached from that, but that was the visualized data was not the one that we evaluated. So we took the data from the Viken system there. So the HoloLens coordinate system had there not the effect. It was not seeing something completely different. It was just the data that we analyzed was not piped through the HoloLens. It was the data we received from the Viken system. That was the one we stored for the evaluation, but also forwarded to the HoloLens to visualize. And to overlap them, we had to do it manually. So the first or the initial positioning of the HoloLens was done with the visual tracking of this that marker, and we had knew exactly where the Viken system coordinate system was, and then for every participant we calibrated that system, because, as you say, how you wear that device deeply affects on how you see that. So we overlaid them manually then to achieve the best individual overlay. What was then the next question?
The essential question maybe is, do you believe that the errors that you see are actually a motor issue or like a human performance issue of what we can do, or is it more largely related to, say, technical reasons like calibration of tracking coordinate systems, calibration of eye distances, resolution, and so on?
Yes, I think it is mostly related to the motor assistance. Maybe not that the data or the amount will have to be looked at differently, especially if there are different sizes. But the overall trend and magnitude of the issues, I think, is still relevant or comparable. Particularly because we used the same system for both the tracking in the virtual condition and in the physical condition. The visualization of the stroke was done in a similar way. The only thing that changed was the physical object or virtual object that was shown.
Okay, one short last question.
Very nice work. I'm curious why, with the physical object, that there was as much spread in the XY traces as there is, because I would have thought that the haptics of keeping the pen in contact with the physical device would have led to very little XY spread for the physical device, but still you can see there appears to be a fair amount.
Yes.
Is that just inaccuracy in the tracking?
No, I think people, when you draw around that, if you try it out, draw around the handle of your seat, it's, well, especially if there are roundings and if it's not a flat surface, you sometimes lift off, especially if, we asked participants to use a regular drawing speed, keep the precision in mind. We don't we haven't told them, well, go around as fast as you can, but also not really try to do everything very, very slowly, just, well, as you would hope to be able to draw. In that instance, they lifted off a couple of times. That's also the reason why we did not ask people to really take a pen and draw on the object to have the ground stroke, because it would not then be able to visualize drawing in midair then basically.
Okay, so if there are any further questions, please move them to the coffee break or to the lunch break. I think Philipp will be happy to take them and answer them. So thank him again for this nice talk. Thank you. And during setting up, there's just